Hello, in this session, we are going to solve one numerical on effect of gyroscopic couple on shapes using method 2. Now, in previous lectures, we have seen how to determine the effect of gyroscopic torque on ships during the steering and pitching phenomena. Okay. Let us revisit the nomenclature of shape. So, this is front view of the shape, this is top view, and this is side view. Okay. Front end is called as bow or fore end. Back end is called as stern or aft. Left hand side of the ship is called as port and right hand side is called as starboard. This is the longitudinal axis about which the rotor or propeller of ship rotates. The ship can steer towards the port side or starboard side. We call this as steering, and this steering motion is visible in top view. And the steering takes place in horizontal plane, and when steering takes place, it will change the direction of axis of spin, that is axis of rotation of the rotor, and hence it will produce the gyroscopic torque. Another type of motion is the up and down motion of the fore end or up and down motion of the bow about the axis perpendicular to this plane. Say the axis passing through this point, and this up and down motion of the bow is called as pitching. Pitching also changes the direction of spin axis, and so it will induce the gyroscopic torque. Now there is third type of motion which is visible in the side view. Say you are looking at the ship from the stern end, and you will observe that the ship is oscillating about its longitudinal axis. Okay. This motion is called as rolling motion of the ship. During rolling motion, there is no change in the direction of axis of spin. So it will not induce the gyroscopic torque. So in case of naval ships, gyroscopic torque is produced only during steering and pitching, and it is absent during rolling motion. We know that we can find out the magnitude of gyroscopic torque using this equation I omega omega p, where I is the moment of inertia of rotating parts, omega is the spin angular velocity, that is velocity with which the rotor is rotating, omega p is the precision angular velocity, velocity with which ship is steering or pitching. Now during pitching, we assume that pitching of ship takes place with simple harmonic motion, which can be represented by this equation, theta is equals to phi sine of omega naught t, where theta is the instantaneous angular displacement of the ship during pitching, phi is the amplitude of swing in radians, omega naught is the angular velocity of SHM, which is given by 2 pi divided by the time period of the swing or pitching. Omega p is the rate of change of angular displacement of the ship during pitching. We called it as precision velocity, which is time derivative of angular displacement theta. So when we differentiate this equation, theta is equals to phi sine of omega naught t, we get phi omega naught cos of omega naught t. Now omega p will be maximum when cos of omega 0 t is maximum, that is when cos of omega 0 t is equals to 1. So we can say that omega p max is equals to phi into omega 0. So if the ship is pitching with maximum angular velocity, the corresponding maximum gyroscopic couple will be is equals to I omega p max, that is I omega p max is phi into omega 0. This is the value of maximum gyroscopic torque acting on the ship if it is pitching with maximum precision velocity. Now let alpha be the angular acceleration of precision, which is obtained by differentiating the omega p with respect to time. So when we do that, when we differentiate this equation with respect to time, we get the angular acceleration of precision, so which is equals to minus phi omega 0 square sine of omega 0 t. Now this will be maximum when sine of omega 0 t is equals to 1. That means we can say that maximum angular acceleration of precision is equals to minus phi omega 0 square. Now this equation will help us to find out the magnitude of gyroscopic torque and precision velocity and acceleration during precision of the ship during pitching. So let us solve one numerical. The rotor of a turbine of a ship has a mass of 2500 kg and it rotates at 3200 rpm counterclockwise as seen from the stern end. Stern end means back end. The rotor has radius of gyration of 0.4 meters. You have to determine the gyroscopic couple and its effect when the ship steers to the left in a curve of 80-meter radius at a speed of 15 knots. This is the linear speed of the ship, where 1 knot is equals to 1860 meters per hour. Number 2, the ship pitches 5 degree above and below the normal position and the bow is descending with its maximum velocity. The pitching motion is SHM with a periodic time of 40 seconds. And number 3, the ship rolls at the instant at 0.4 radian per second clockwise as seen from the front side. Let us extract the data from the problem statement. Mass of the rotor is 2500 kg, so m is equals to 2500 kg. Speed of rotor is 3200 rpm, so we indicate it by n is equals to 3200 rpm. And direction of rotation of rotor is counterclockwise as seen from the stern end. Next, radius of gyration of rotor is 0.4 meters. So we take k is equals to 0.4 meters. We will solve for the first case. The ship steers to the left in a curve of 80-meter radius at a speed of 15 knots. So what we want to find out is magnitude of gyroscopic torque, which is equals to I omega p, where I is equals to mk square, moment of inertia of rotating parts. Omega is the spin angular velocity of the rotor, which is 2 pi n upon 60, and omega p is the angular velocity with which the ship is steering to the left, which will be equals to linear speed of the ship divided by radius of turn. We know that the ship is taking a turn of 80-meter radius towards left. So this is capital R. Linear speed of ship is V, 15 knots. We want to find out the angular velocity with which the ship is steering, that is omega p. We know that V is equals to R into omega. Okay. We have studied the circular motion. So we can find out omega p as the ratio of linear speed of the ship divided by radius of turn. Let us solve for this. So I equals to mk square, mass is 2500 kg, and radius of gyration is 0.4, so 0.4 square. We get I is equals to 400 kg meter square. Next, spin angular velocity, that is velocity with which the rotor is rotating. The speed is given in RPM as 3200. We will convert it into radian per second using this equation. Omega equals to 2 pi n upon 60. So n is 3200. We get spin angular velocity as 335 radian per second. We will find out the precision angular velocity, velocity with which the ship is steering to the left in a curve of 80 meter radius at a speed of 15 knots. So omega p is equals to v by r. So let us convert this linear speed v into meter per second. So 15 knots into 1860 meters per hour, and this 60 will convert hour into minute, and this 60 will convert minute into second. So we get v is equals to 7.75 meter per second, linear speed of the ship, and radius of turn is 80 meters. So we get omega p is equals to 7.75 divided by 80, that is 0.97 radian per second. The magnitude of gyroscopic torque is I omega omega p. So 400 into 335 into 0.97 gives the magnitude of C gyroscopic torque 12981 Newton meters. Now this amount of torque is acting on the ship when it is steering to the left in a curve of 80 meter radius. Now we will find out its effect. So we are looking at the rotor from stern end. First of all, we place the coordinate system consisting of three axes x, y, z. We always place the observer along the x-axis. Now we will draw the ship along the x-axis in such a way that its stern end is facing towards the observer, because we are looking from the rear side or stern end. So I have drawn the ship along the x-axis in such a way that stern end is facing towards the observer. Now while looking at the ship from stern end, the rotor is rotating counterclockwise, and we will assume that the rotor rotates about x-axis. So x-axis is the spin axis. So first of all, we will mark the direction of rotation of the rotor using circular arrow. So as seen from the stern end, omega is counterclockwise. Spin angular velocity in direction. Now to represent the spin angular velocity using a vector, we make use of right hand screw rule. So we curl the fingers in the sense of omega, and the thumb of right hand will point in the direction representing spin vector. Okay. When we curl the fingers of right hand in the sense of omega, thumb will point this way. Okay. So that is our spin vector. So we place this spin vector at the origin, at its tail. Okay, we place the spin vector at the origin. Next, the ship is steering towards left. We call this motion as precision motion because it is changing the direction of spin vector. The ship steers towards left, and the velocity with which it is steering is called as precision velocity. We indicate precision velocity by omega p. Now the plane in which the ship is steering towards left is the horizontal plane XOZ. The ship is steering towards left in horizontal plane XOZ. So XOZ becomes the precision plane because steering is the precision motion. So we identify the plane of precision, and it is XOZ. Ship is steering in horizontal plane XOZ. Now to represent precision velocity omega p using a vector, We again make use of right hand rule. Take your right hand in the precision plane XOZ, curl the fingers of right hand in the sense of omega p, and the thumb will point in the direction of precision vector. So when we do that, when we take the right hand in the precision plane XOZ and curl the fingers of right hand in the sense of omega p, thumb will point in upward sense. And that is our precision vector, which will act along OZ. To find out the active gyroscopic couple vector, we rotate the spin vector, this spin vector, in precision plane in the direction of omega p by 90 degrees. That will give us the direction of active gyroscopic torque vector. So let us rotate this spin vector in precision plane XOZ, that is horizontal plane, in the direction of omega p, this direction. So when we rotate the spin vector in horizontal plane in the direction of omega p by 90 degrees, active gyroscopic torque vector will act along OZ dash. We represent active gyroscopic torque by CG. We are interested in reactive torque, that is which is always opposite to the active gyroscopic torque. So the vector representing reactive torque will act along OZ. We represent it by CR. Now to obtain the sense of this reactive torque, we again make use of right hand rule. We hold the vector representing CR, that is vector OZ, in right hand such that the thumb points this way in the sense of arrow. So when I hold this vector OZ in right hand such that the thumb of right hand is pointing in the direction of arrow, fingers of right hand will turn like this, counterclockwise as seen from the front side. So this is the sense of reactive torque. Now let us find out the plane in which this reactive torque acts. Reactive torque CR will act in a plane perpendicular to its vector. So CR will act in a plane perpendicular to vector OZ, and that plane is plane XOY. So reactive torque is acting in this plane in counterclockwise sense, and its effect on ship will be, it will dip the bow and raise the stern. It will dip the bow and raise the stern. The case 2, the ship pitches 5 degrees above and below the normal position, and the bow is descending with its maximum velocity. The pitching motion is SHM with a time period of 40 seconds. So 5 degree is the amplitude of swing. Okay. The ship is pitching about the transverse axis, that is its bow is moving up and down, and maximum displacement of the bow from its mean position is 5, which is equals to 5 degrees. So we will convert these 5 degrees into radian by multiplying it by pi by 180. So we get phi is equals to 0.0873 radian. Next we find out the angular velocity of SHM, which is equals to 2 pi upon time period. Time period is given as 40 seconds. So 2 pi upon 40 is 0.157 radian per second. Now it is mentioned that the bow is descending with its maximum velocity. So omega p max. We find out maximum precision velocity omega p max, which is equals to phi into omega 0. Remember that we have to take this phi in radians because it is without trigonometric function. So phi 0.0873 into omega 0.157, we get maximum precision velocity as 0.0137 radian per second. Now corresponding gyroscopic torque acting on the shape during pitching is I omega omega p. So moment of inertia is 400, I equals to mk square. We have done that while finding out the value of c during steering. Then precision speed is 335 radian per second, that is 2 pi n upon 60, speed with which the rotor is rotating. Now we have determined omega p max, which is equals to 0.0137 radian per second. So we substitute it here. We get the value of gyroscopic torque as 1837.5 Newton meters. So this is the amount of gyroscopic torque acting on the ship when it pitches 5 degree above and below the normal position. Now let us find out its effect when the bow is descending. Okay. Place the coordinate system, place the observer along x-axis. We draw the ship such a way that its stern end is facing towards the observer because we are looking at the rotor from stern end. The rotor is rotating counterclockwise, so we mark the direction of rotation of rotor using circular arrow. As seen from the stern end, rotor is rotating counterclockwise. Next, we represent this angular velocity omega using a speed vector. For that, let us curl the fingers of right hand in the sense of omega. The thumb will point in the direction of speed vector. So this is the speed vector. We place the speed vector at the origin, at its tail. Now the ship is pitching downwards, means its front end, that is its fore end is moving downwards, and this will change the axis direction of axis of spin. We call this as precision motion, and the velocity with which the ship is moving downwards is precision angular velocity omega p. So at this instant the ship is pitching downwards, its bow is going downwards, and this motion of the bow going downwards takes place in vertical plane x o y or x o y dash. This omega p precision velocity acts in vertical plane x o y dash. This is our precision plane, the plane in which the motion of the bow going downwards can be represented. That is the plane in which omega p acts. Okay. So this is the precision plane. Now we will represent this omega p using a precision vector. For that, take your right hand in the plane of precision x o y dash, curl the fingers of right hand in the sense of omega p, and the thumb will point in the direction of precision vector. So when you take the right hand in the precision plane x o y dash and curl the fingers in the sense of omega p, the thumb will point this way. That is the precision vector. We place the precision vector at along the axis OZ. Now to find out the direction of active gyroscopic torque, we again rotate the spin vector, this spin vector, in precision plane x o y dash, vertical plane, by 90 degrees in the direction of precision velocity omega p. So let us do that. We will rotate this spin vector in vertical precision plane x o y dash by 90 degrees in the direction of omega p. When we do that, we get the direction of active gyroscopic torque vector. That will be along axis OY. It's very simple. We have to rotate the spin vector in precision plane in the direction of precision velocity by 90 degrees to get the direction of active gyroscopic torque vector. Now reactive torque is opposite to the active torque, so it will act along OY dash. Now to find out the sense of reactive gyroscopic couple, we hold this vector representing CR in right hand such that the thumb of right hand is directed in the direction of arrow. Hold the vector representing CR, that is vector OY dash, in right hand such that thumb is pointing in the direction of arrow. The sense in which the fingers have turned is the sense or the direction of CR, and it will be clockwise as seen from the top side or as seen in the top view. Okay, when you hold this vector in your right hand such that thumb is pointing this way in the direction of arrow, fingers of right hand will be curved like this. And that is the sense of CR. Now let us identify the plane in which reactive torque acts. Reactive torque CR will act in a plane perpendicular to its vector. So this quantity CR will act in a plane perpendicular to vector OY dash, and that is the horizontal plane XOZ. So CR is acting in horizontal plane XOZ. Okay, angular quantity always acts in a plane perpendicular to its vector, and XOZ is the plane perpendicular to vector representing CR. So CR will act in plane XOZ, horizontal plane, and effect of this will be it will try to steer the ship to the right side or starboard side. Okay, thank you.